In the vast expanse of the universe, humanity has always looked to the stars with wonder and curiosity. We have ventured beyond our home planet, explored the moon, and sent robotic emissaries to distant corners of our solar system. Today, we're closer than ever to leaving the Earth. But there's a sobering truth. Rocket engines, the very technology we've relied on for space exploration, will never take us to the stars. Let's start with the basics. Rockets work by expelling mass, fuel out of their engines at high speeds. Thanks to Newton's third law of motion, every action has an equal and opposite reaction. Propelling the rocket forward, this principle has worked wonders for getting us to the Moon, Mars, and even interstellar probes like Voyager. But here's the catch. Space is big. The nearest star system, Alpha Centauri, is over 4 light-years away. That's about 40 trillion kilometers. To cross that distance with current technology, it would take tens of thousands of years. The faster you want to go, the more fuel you need. But as you carry more fuel, the rocket gets heavier. Even with theoretical advances, rockets simply can't store enough energy to bridge interstellar distances in a reasonable time frame. Even if we solve the fuel problem, there's another challenge: the speed of light. According to Einstein's theory of relativity, as an object with mass approaches the speed of light, its energy requirements increase exponentially. To go even 99% the speed of light, you'd need almost infinite energy. Now, you might be thinking, what about new propulsion systems? Ion thrusters, for example, use electric fields to accelerate particles to high speeds. Solar sails use sunlight as propulsion, and nuclear fusion or fission engines could theoretically provide far more energy than chemical rockets. But even these advanced systems face the same fundamental problem. They're still bound by the need for fuel and the limits of light speed. While today's propulsion systems might seem limiting, tomorrow's technology could break these barriers. In 1994, physicist Miguel Alcubierre proposed a theoretical framework for faster-than-light travel, not by breaking the light-speed barrier, but by bending space-time itself. The warp drive compresses space-time in front of the ship and expands it behind. The ship itself remains in a bubble of normal space, so it's not technically moving faster than light. It's the space around it that's doing the heavy lifting. The math behind warp drive is fascinating and a little intimidating. Alcubierre's equations rely on Einstein's general relativity, which describes how mass and energy distort space-time. By creating a warp bubble, a ship could theoretically travel faster than light without violating physics. But there's a catch. To generate this bubble, you'd need negative energy, something we've never observed in usable quantities. And the energy requirements? Astronomical. Early estimates suggested you'd need more energy than exists in the universe. Recent refinements have brought that number down, but we're still far from practical. But history has shown us that what seems impossible today can become reality tomorrow. Organizations like NASA and private companies such as SpaceX and Blue Origin are pushing the boundaries of what we thought possible. The stars aren't just distant points of light, they're destinations, and they remind us that humanity's greatest strength has always been its ability to look beyond what's possible.